Now let's go with the characteristics of PN junction diode. Now what we have, as we have learned from the previous video, that what are the conditions for forward biasing of a of a PN junction, and what are the conditions for the reverse biasing of a PN junction. Now let us try to characterize, see the forward bias characteristics of forward biased characteristics of diode. So now we understand what are the forward characteristics. We have a PN junction, okay, and let us have a milliampere meter here, and let us have uh, let's have a voltmeter that will measure the voltage. And now let's have a rheostat, by virtue of which we can control the potential difference. And let's have a key. Say this is key, and let us connect the circuit like this. Now here we will join it like this. Now we have a situation here, and we have a PN junction, and we have a rheostat by virtue of which we can start from 0 volts and measure the current that's developed across this PN junction, and at the same time we can calculate the voltage. Now if we try to plot the behavior, the graph, the graph between the current and the voltage here. So we have voltage and we have current. Now this current is forward current in milliamps, and so this is the voltage. So now what is forward biasing? So we are forward biasing it here, and because the positive terminal is connected uh, to the P side of the PN junction, and negative terminal is connected to the to the N side of the PN junction. So the graph that we will have, and that shows the variation of current with respect to the variation in the applied voltage, and we call this as forward biasing characteristics of PN junction. And for that we have the circuit diagram for the forward biasing of the PN junction, and we would like to plot the graph between the voltage and current for this PN junction. Now when the voltage V is 0, what's going to happen when voltage is 0? That means S is not closed. I mean this K is not closed. The diode does not conduct due to the junction barrier. That's clear. Uh, and and the diode current is 0. Now, as the forward battery voltage is, as this voltage is increases, the barrier potential starts decreasing, and a small current begins. I mean, so up to some limit there is no current because of the barrier potential. Then there is a small rise. There's a small increase in the current. It begins at some point. The forward current increases slowly at first, but as soon as the battery voltage increases, the forward current increases rapidly. So it goes up very fast. Now the battery voltage, I mean, at which the forward current starts increasing rapidly. So let us have it here. Now this voltage is knee voltage. We call this voltage as the knee voltage, or threshold voltage, at which the current in the PN junction starts increasing exponentially. So we call this thing uh, as the knee voltage. Now the battery voltage. Uh, so so uh, for germanium, we have a different knee voltage, and for 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 silicon we have a different knee voltage. So these values are all already talked about. It's nearly zero point 0.2 volts for germanium, and it's nearly zero point 0.7 volts for silicon when forward voltage is above the knee voltage. So that's the condition here. Now, uh, how should I conclude this? Is you can see that the voltage current graph for this diode is not a straight line. It's not going straight, right? So if it is not a straight line passing from the origin, thus diode does not obey Ohm's law, and in other words, it means a diode is a non-ohmic conductor because it does not behave exactly in the way as we have a situation in case of metals, where we apply the potential difference, and as long as we apply the potential difference, the current starts coming. Here we have a concept of potential barrier. So the resistance across the junction of the diode is large. It is large below this knee voltage. So the opposition is large, okay, and the resistance across the junction of the diode decreases above this knee voltage. So when we reach to this knee voltage, the resistance it goes down. So one point should be borne in mind here is that there is a limit of current that can pass through the diode without damaging it. So a high current through the diode produces large amount of heat, which may damage the diode. Now, so this is our forward biased characteristics of the PN junction. So in the similar way, we would like to go with what's called as we would like to discuss the reverse biased characteristics of the PN junction diode. So now reverse characteristics of diode. Okay, so the point is very much clear. We have a PN junction, and the PN junction, we have to measure the current in microamps here, because we are reverse biasing it. That means we are giving a negative terminal to the positive of the PN junction, and we are giving positive terminal to the N side of this terminal, and we make use of a rheostat. So let it go the way we showed it in the previous diagram. So we have a situation like this, and a battery. So here we have negative terminal to be connected to the P side, and positive terminal to be connected to the N side. So we could think of a key here. Say here we have a key K. Okay, so this is the circuit diagram for PN junction in reverse bias mode. We can see that the negative of the battery is connected with the P side, and the positive is connected with the N side. So now what we are supposed to do? So what are the reverse characteristics of a PN junction? Uh, that means you have, if you draw the graph between the current and voltage in the reverse biasing mode, the graph that you will obtain will refer to the reverse characteristics of this what is called as PN junction diode. Now, to look for this and to have some some discussions on this pattern is is that when a PN junction is reverse biased, the majority charge carriers that we have talked about in P and N region, they are repelled away from this junction. So you have a junction, if you remember rightly back. So there is increase in the size of depletion layer when we reverse bias when we reverse bias the PN junction. So that's the case that we understand. But so there is a small current due to the minority carriers. This current attains its maximum saturation value immediately and is independent of the applied reverse voltage. Now it depends on the temperature of the junction diode. Now what is it? That means if I have to plot, if I want to plot, because I'm giving here the reverse voltage. So we have the small magnitude of current. Now this small magnitude of current is by virtue of say this is V, so this will be minus V here. So this is the current. Okay, so this reverse voltage is because of the minority charge carriers in the PN junction. So this as this reverse voltage is increased to certain value, so we have a rheostat and we can use it to enhance the voltage across the PN junction. As we reverse the voltage, as this reverse voltage is increased to some value, what we call as breakdown voltage, what we call as breakdown, the large amount of covalent bonds in P and N regions of this PN junction are broken. As a result of this, electron hole pairs are produced, which diffuse through the junction, and hence there is a sudden rise. There is a sudden rise in the reverse current. Right? Once the breakdown voltage is reached, the high reverse current, and this current may damage the ordinary junction diodes. That current is produced at such a voltage, what is called as the breakdown voltage. So this side of the graph is showing us the reverse characteristics of the PN junction, and if I plot the same thing regarding the forward characteristics, it was something like this. And here we have the knee voltage, right? So VK, V knee, and here we have the breakdown voltage, VBR. So what is that? That's breakdown voltage. Breakdown voltage. Okay, so so this rise in the current in the reverse direction is exponential. It's very large. It's very fast. Now, semiconductors are highly temperature sensitive, as we have talked about them. That they are sensitive in terms of temperature because the electrons they attain the thermal energies, and by virtue of these thermal energies, more of these electrons become available at the conduction band. So they are sensitive to the temperature. So current passing through the PN junction diode produces heat, which affects the diode. When large current passes through the PN junction diode, a large amount of heat is produced. Now, this heat can be sufficient to damage the diode. Thus, PN junction is a current sensitive device. So we should keep that thing in mind. It's a current sensitive device. Now, if we have to define some basic terms regarding the PN junction, we have here number one is what is called as static resistance, DC static resistance. Okay, so in a junction diode, current does not linearly follow applied voltage, so it does not obey Ohm's law. What I'm talking about. Thus a junction diode is an example of non-ohmic conductor. It's not an ohmic conductor. The resistance of the diode is the function of operating current. That's clear. So diode has two possible resistances. Now, one resistance is what is called as static resistance. So what is this static resistance? It is simply it is defined as the ratio of the DC voltage that's across the diode to the direct current flowing through it. So this DC static resistance is simply, if I call it RS, it is simply V by I. Right? So this is the first point. The second thing is AC or dynamic resistance. So we talk of two types of resistances in case of PN junction, and this is probably written as RD. Now this RD is the change in the voltage potential difference across the PN junction divided by the change in the current. So, so this is the situation where we have understood that on characterizing a PN junction diode, we have two modes. One is the forward biasing mode, and another is the reverse biasing mode. In forward biasing mode, we have a non-ohmic behavior between voltage and current, and in reverse biasing mode, we have the magnitude of current is extremely small. You can see here, but if we increase the reverse voltage, then at some voltage known as breakdown voltage, the bonds between the atoms break, and they produce large number of electron hole pairs, and they tend to move under the potential difference, reverse potential difference, and there is exponential rise in the current in the reverse mode.